in this exercise we have this function, and we have to calculate the disjunctive normal form, the conjunctive normal form, the disjunctive canonical form, and the conjunctive canonical form. We can see that the function is not normalized. It's not a sum of product or a product of sums. So we are going to start applying some of the axioms and theorems of the Boolean algebra to reach the normalized ways of representing the function that are neither the ways of representing the function the exercise is asking. So first case, we can start by applying the De Morgan's law to this negation and this negation. So here we apply the De Morgan law. So we break the first product, so maybe you haven't seen how I applied here the De Morgan's law, because it's applying twice the De Morgan's law. I'm going to do it here just to show how to do it. Sorry. So I apply the De Morgan's law here. So I break the line, and this product has converted into a sum. But now I'm going to apply here again the De Morgan's law. So this is what we have in the equation. Now in the next step we are going to apply the distributive property, but apply to the sum. I'm going to remember this. This is the distributive property that we are interested in. If we have a variable that is sum to a product, we can have two sums of the variable with both of them independently. So we have here two sums of the variables with one of the other and the other. So we are going to apply this distributive property here. Okay, so we'll see. So this is the result of applying the distributive property in this term. So now we are going to apply again the distributive property, but in this case. So we are going to have the C include in all these terms and the D include in all these terms, in a way that we are going to have 8 new terms. So we include the C. And now we include the D in the rest of the terms. Sorry, this is not a sum but a product. So this is the function. Now we are going to see if we can eliminate or reduce some of the sum terms that we have. We are going to see that we can use the complementation axiom and the idempotent law. I'm going to remind you this. The complementation is this: if we have a variable and the same variable negated, is 1 in a sum, but it's 0 in a product. So we are going to look for terms that have the variable negated and non-negated. And as well, we are going to use the idempotent law, that is, let me check, here. This is the idempotent property is a theorem, if I don't remember. Is here, the idempotent law. So if we have a variable multiplied by itself, is the variable. So if we have the variable repeated, we can eliminate one of them. So we proceed with the function. So we can see that here we have C and C negated. So this is 1. Here we have C repeated, so we can remove it. We can remove as well this double C, and I think that is all that we can do in this expression. No, here we have a double D. So we continue writing the function, but with all modifications. And now, to simplify the expression, we are going to use the absorption law. I'm going to remind you this law. This is quite powerful. So we have some terms, so we are here. If we have several sum terms, but we have smaller sum terms, and they are repeated in another sum terms, the smaller can absorb the larger, and we are going to have the smaller. So this is a powerful tool to eliminate some of the terms. We are going to see if we have some terms that are suitable for this absorption law, and we have some of them. For example, if we pay attention to this sum term, A negated C, we can find A negated C here, A negated plus C. For example, A negated C here. For example, B negated C, we can find B negated C here. So we can absorb these larger sum terms. So we absorb them. Well, if I say that we absorb them, is that they are not going to be present in the expression anymore. So they are going to be out. And I think that we cannot have absorbed any other term. So we are going to simplify the function. So we have A negated plus C, B negated plus C, A negated but B negated plus D negated, and finally C negated plus D. I don't see how to minimize this expression more, so since we cannot apply more action or theorems to make it smaller, we have just finished. And this is a product of sums. So we have the conjunctive normal form of the function. So now we are going to look for the rest of the representations. For example, if I start with this expression here of the function, we may apply the distributive property, but the other one. Distributive action here, but this one. And we can apply this distributive property to these products, for example. So we are going to start applying the distributive property to these products. So we are going to have this that is multiplied by the rest of the term. As you can imagine, I'm looking for the disjunctive normal form. So we are going to apply again the distributive property with this product. I recommend you to order the variables. When you have several variables in a product term, I recommend you to order them, because this way you are going to see in an easier way. For example, if we can apply the absorption property, etc. It's easier to see if they are in order. So I'm going to order them. So we continue, and we have just ordering the variables. Okay, we have this. And I think that I'm not forgetting none of the terms. And now we have to look if we can simplify the function by removing some of the terms. We are going to use again the idempotent law to eliminate some of the variables, also the complementation axiom. So if we have the variable and the variable negated, we have 0, and as well, the absorption law. The absorption law is also powerful. So we are going to identify these terms that are suitable for these properties. So, for example, the idempotent, we can eliminate this A, but and this B, I think. Yes, not the A, but just the B. Sorry, just the A by the idempotent law. Here again the A, here the B, here the B because it's repeated. Here we have the C and the C negated, so we can remove the term because it's 0. And here we have again the C and the C negated. So by the complementation axiom, it's going to be 0. And now we can try to use the absorption law, because we have this smaller term, so we are going to look for this term in the other product terms. We can find it here, so we absorb this term. We can find it here. I think it's all. It's all, I think. So we are going to write the product terms we have. So we have this one, this one, I realized that I made a mistake here, because this is C negated. Here we have C negated. So we can apply the absorption law as well to these terms. Here we have A, B, C, but we have here A, B, C as well. So we can apply the absorption law. And here we have A negated, B negated, D. That is the same as this. A negated, B negated, D. So we can absorb one of the terms. So finally, we have only this term, and this term. So we have this expression that I find the most reduced possible. So this is a sum of products, so we have the disjunctive normal form. So we proceed to calculate the canonical forms. As you remember, we have this expression. In this product term, we need the D variable, so we can multiply by D plus D negated, because this is 1. This is the way of obtaining the canonical disjunctive form, starting with the normal form. So in the other product term, we need the C, so we multiply by the C plus the C negated. And in the other, we need the A and the B. So we have to apply the distributive property to this expression, and we are going to have all the mean terms of the canonical form. So if we apply the distributive property, we are going to obtain the following. I'm going to delete this to have more space. So now we are going to look for some reduction, if it's possible. And we can find that this term is repeated. So we can apply the idempotent law. This is the same as this. okay, and we can also apply the idempotent law to this term that is as well repeated is here. So I don't see more terms to reduce, and we have here the disjunctive canonical form. We can identify the mean terms. This is 0, 0, 0, 1, so it's the mean term 1, 0, 0, 1, 1, mean term 3. I think I forgot one mean term when doing the multiplication. We have this combination as well. Just check it, okay? But I think that we need this one. Yes, it's here. Applying the distributive property here, we have this mean term. So here we have this is okay. This is eliminated. Okay, I see the problem now. The thing is that I'm copying from my documentation and I copy twice the same mean term. So here I had the 0 mean term. Sorry. So this is eliminated by the idempotent law. Here we have the 7. The 11 and the 15 mean term. So this is the canonical form, the disjunctive canonical form, and we still have to calculate the canonical conjunctive form. But if we have the canonical disjunctive form, it's quite direct, it's quite straightforward. We don't have to do any algebraic manipulation. We have here that the function is the sum of these mean terms. So the function expressed as a product of max terms is going to be the zeros. So we take the gaps of the mean terms. It's going to be the following. So this is the conjunctive canonical form. So we have the solution of the exercise. We have all the forms the exercise asks. Well, it's just applying the axiom and the theorems, and once we have the canonical, one of the canonical form, we can directly obtain the other. We have solved the exercise.